So hello everyone for this last lecture. Right, so last time I was talking about how to compute expectation values of product of traces in the planar limit. So the larger limit, exactly what free probabilities want to compute. Right, and so a single trace with an arbitrary number of, with a product of an arbitrary number of powers of M1 and M2. And the result is that this is a sum of our link patterns with a certain coefficient of product of these functions, which correspond to having exactly two, 1 power of M1 and 1 power of M2 in a single trace. And I said last time that I would give a formula for C sigma, and here it is. So if sigma, so let me give this example. If sigma is the permutation represented by the yellow arrows here, so each time it goes from an x, so sigma goes from an x that are the red dots to y that are the blue dots. And the value of C sigma is a rational fraction that depends on the variables x1, x2, and so on. It's a universal rational fraction, and its value is very simple. It's a product over all faces of this graph. So for example, this is a face. You see on this face starts with x1, then y4, then this would be x5, xn, yn. Sorry, no. This is yn minus 1. So this one is yn minus 1, xn, yn. So these are the variables along the face. And the value of the face depends only on these variables. And I call it, so I have 3 pairs of xy variables. So I have 6 variables, but 3x and 3y's on this face. So I call it f3. And it's a function of x1, yn, xn, yn minus 1, x5, y4 in this order. So you follow the variables along the face in the order given by the arrows. If you and here, for instance, on that face, the order given by the arrows is the opposite. So be careful. In that face, you would have to compute an f3 of x1, y4. Sorry. Okay, so, well, it's just you have to be careful about the, sorry, you should rely on the order, on the orientation is the one given by the boundary, and you have to go from an x to a y, and here from an x to a y.
I think, Bertrand, you got muted.
Okay.
And now you're back.
Yeah, I'm back, but it seems that there is a problem with the microphone. I hope it's going fine. Okay, so yes, so the value of C sigma is a product of face of values given by faces, and in each face you have to follow.
You're muted again. Everything. And okay, let's see. Have to call IT. Okay. If at least there were like a piano accompaniment in the background. Oh, we can hear you now.
T'aurais pu prendre l'autre micro, le micro à main. Ouais, je veux bien commencer avec le micro à main. Non, là, ça marche. Ah.
Or we can hear something.
Can you hear me now?
Yes, you're back.
Okay, so we are going to change the batteries, so it might cut again. So yes, so I was saying, okay, this is the final formula. It's a product of our faces. So value C sigma is a product of our faces. On the face values, obey this recursion. You start, so a face of length 1 value is 1, and then you have this recursion, and you find some nice rational functions. They all have cyclic symmetry, although it is not obvious from this formula because x1 seems to play a special role. But in fact, it is, you can prove that it is indeed cyclically symmetric. So now let me summarize what we have already found. So what we would like to compute is the generating function for maps we've given with a certain number of faces, which I call the boundaries, and with certain boundary conditions. And we would like to compute arbitrary genus. So what we have computed so far, so far I always represented the faces like that. So this is a marked face, and it has a certain number of plus and minus and plus and minus minus and so on. And it is included in a bigger map. There can be other marked faces somewhere. Now let me put, and the faces are labeled 1, 2, and so on. Let me put the face 1 on the exterior, and in fact what I will do now, from now on, is I put the marked face, so the face 1 on the exterior. And so all the map is inside. And in particular, the other faces, which I also represent by circles, are inside. And there can be a genus, and let me represent it by handles. Okay, so this means genus G, meaning that there are G handles. So let me represent things that way, and each of these also faces has a certain number of plus, minus, and so on. So this is what we would like to compute. And also remember that if I have L1 faces of sign plus followed by L tilde 1, by L tilde 2, okay, and we want to make now a sum over L1, and we want to multiply by x1 to the L1 plus 1. Same thing with 1 over y1 to the L tilde 1 plus 1, and so on. So in fact, instead of representing the plus and minus, let me represent directly the variable x1 with a red dot and y1 and x2, y2, and so on. So in the end, let me just represent all my objects like that. So we have a certain number of x and y's that alternate Okay, and each dot like that means one of the variables xi's or yi's. Okay. The faces are the boundaries are oriented. Okay. But the one which is outside, of course, has the opposite orientation, or in fact, it has the same orientation, but the center is at infinity. And beside, we would like also to compute such objects where possibly some of the marked faces are not mixed. And when a marked face is not mixed, for instance, it contains only plus, it would correspond to a circle with only a red dot. In fact, instead of writing a circle with a red dot, let me just put the red dot. So I also want a certain number of red dots and a certain number of blue dots corresponding each to some variable x, and which mean that we are taking traces of single powers of M1 or single powers of M2, so non-mixed. So this is the most general object we would like to consider. In the language of random matrices, this is equivalent to computing something like trace of M1 to the L1, M2 to the L tilde 2, and so on, times other product of traces, and times possibly M1 to the K1 without M2, and so on, and expectation value of this, cumulant. Okay, cumulant guarantees that we have is equivalent to having connected maps only, and we want to expand that to order G in the large N expansion. Order 0 means planar, and so on. So this is just a notation for that, or in terms of resolvents, this would be trace of 1 over x1 minus m1, 1 over y1 minus m2, and so on. Okay, some trace of 1 over x minus m1 alone. Okay, and again, expectation value cumulant to order G. So this is just a graphical notation for these quantities that we would like to compute. So far, what are the ones that we have computed? We have computed W01 of x, which in my notation is a sphere with a single point, x. And we have computed it, and in my notation, it was v prime 1 of x minus y of x, where you remember that y of x was a solution of the algebraic equation x y of x equals 0. Okay. We have also computed the one that I will call x of hy, which is a single, which is planar, 0, 1. 0 means planar, 1 means a boundary with exactly one pair of x and y. So this is my x, this is my y. And it is also given by the spectral curve. It was E of xy divided by x minus x of y divided by y minus y of x. We have also computed the planar one with an arbitrary number of plus plus and minus. And remember, this one was the sum over C sigma product of H01 of xi y sigma I. Okay, so we have computed these. Now we want to compute all the others. First of all, let me start by speaking about the non-mixed ones. So the non-mixed. And that's where we shall need, basically, in the non-mixed are typically what I call WGN, which with this way of representing things is genus G and N red points. Okay? And in fact, it is given by topological recursion. So let me recall that topological recursion is a procedure that to a spectral curve it associates a sequence of differential forms that are called omega gn. And it turns out that basically this is the answer to our thing. If we take a spectral curve, we take the curve of equation x of x, y equals 0. Let's take that as our spectral curve. And the omega gns we get from the topological recursion are our WGNs, or more precisely, more precisely, let me say the following. Let me plot in the xy plane. Let me plot the set of all points such that E of xy equals 0. It's a curve. So it's a curve. But you should keep in mind that x and y are complex variables. So in fact, it is 2-dimensional times 2-dimensional. So in fact, you plot it in 4 dimensions. And it is a complex curve. So the curve itself is 2-dimensional, real, 1-dimensional complex. It's a complex curve. And you should think that it is in fact a surface. But let's do this representation. Now, let's take a point P on the curve. A point P on the curve has a projection x of P, and it has a projection y of P. And in fact, the same point on vice versa. If you take a point x on the x plane, it has several pre-images. It has P, but it has another point here. And in fact, usually, in general, the number of pre-images is D. You have D pre-images, the degree of the potential V1. And on the other direction, you have D tilde pre-images by Y. So here you have D tilde. And, sorry, D in that direction. So a point has several pre-images. What this equation tells you, what is the function y of x? So if you take a point in here, you should choose one of the pre-images and compute its y, and that's what y of x is. So if you take a point P, then this is y of P. So in fact, the function y of x is a multi-valued function. Typically, if you are familiar with it, it would contain square roots and things like that. It is a multi-valued function. But if you think of it in terms of points in the curve, points on the curve, it is mono-valued. So, I mean, for each point, there is exactly one value of y. What makes it multi-valued is because you want to, it's just because there are several p's corresponding to the same x. That's the only thing that makes it multi-valued. Given a point, it is mono-valued. So from now on, I will retranslate everything that I was doing with the x variables. I will retranslate it into variables on the curve. So for instance, when we had WGN of x1 and so on, in fact, let me take a point x of P1, x of Pn. Let me make it a differential form, dx of P1, dx of Pn. And now, let me call it omega gn of P1, Pn. Now it's a differential form on the curve. And the theorem is that these are, so the theorem is that the omega gns defined by these correlation functions are the same that the ones you get by topological recursion from the curve E of xy equals 0. So I'm not going to prove this theorem, but basically this means that all these guys are known by topological recursion. Now we want to compute the general guys. Before doing so, let me retranslate everything that I was doing so far. And in particular, let me retranslate this H01. Let me call it H of PQ. So it's the same as before with this X. So basically, it will be the same as H01 of X of P and Y of Q. and let me call it h of pq, and so it is the same thing as e of x of p y of q divided by x of p minus x of q times y of p minus y of q. So this is the ingredient that we shall need. So now let me go to the general case. So we can, so what we found, and this was Orentin's thesis, in fact, in 2007. It was really one of the main things we did during Orentin's thesis. So we wanted to compute correlation functions corresponding to these guys. So let me start with P1. And here I move from x variables to y variables with a permutation pi. So let me call this one q pi of 1. The next one, so the next one will be p pi tilde inverse of pi of 1. Okay, the next one will be a q. So you move from there to there by pi tilde inverse. You move by pi tilde inverse, and so on, until you reach a cycle, the end of a cycle, and you have several other cycles. So basically, each boundary is a cycle. So each circle is a cycle of pi tilde inverse pi. In fact, I followed Roland Speicher's lectures, and in fact, Speicher has a different way of encoding this kind of information by this pair of a partition and a permutation, but I think this is more or less equivalent. I mean, it must be equivalent. But I prefer this one because we can make matrix operations work in this framework. So, and in the other boundaries, we also have a certain number of p's that I put in red, and some q's that I put in blue. Okay, we can have many of them. Sorry. And we can also have a certain number of just red points that correspond to non-mixed traces, and a certain number of blue points that correspond to non-mixed traces of M2. And this is the most general guy we would like to compute. And sorry, on genus G. So a certain number of handles. All right, so there is a recursion formula to compute this guy, and the value of this generating function will be equal to a sum of other terms, and the way to find them is the following. We start between P1 and Q of P1, Q of pi 1. So we start from the first point, P1, sorry. So remember, the points are labeled, and the boundary that I put to the exterior is the one that contains the point P1. Okay, I will assume it always contains the point P1. I mean, it is the one that contains the point P1, and I start from there. And I will start by cutting, and now I will cut the surface, so I will draw a line that cuts the surface. This line starts between red and blue, and it must end somewhere. So let me put, so it starts between a red and blue, and it will end somewhere else between a red and blue. So what are the different possibilities to cut? So one possibility is that I start, so where is my piece of chalk? So one possibility would be I start here, and I end up there. Now recut with scissors, cut this surface, and you will get a new one that will have one more So it will have one less boundary, same genus, one less boundary, same genus. Okay. So let me put Q pi of 1 here, and so on. And here, let's say this was a P index K here, and so here was the Q index pi of K. So we have Q index pi of K, and so on. And the last one here is P index K, and so on. Okay, so this is the new surface that we have, and we have a certain number of points. Okay, so this is another of the generating functions. And now the only thing is that here I will not put the variable P1, I will put another variable that I call R. Okay, we cannot read. Okay, and I will make a sum over R, an integral over R, dx over R. In fact, this integral is in fact a residue when R is at some point, and times a certain function. This function will be, so I should have left more space. So let me put it on the right, times, let me leave some space here, dx of R, and here I take the function h of P1 Q pi of 1 divided by h of R Q pi of 1, x of P1 minus x of R, y of P1 of y of Q pi of 1 minus y of R. Okay. And here I also multiply by 1 over x of R minus x of pk. And I will take where I take the residue. But this is one of the terms that will give me the answer. But there are other terms, because there are other ways to cut the surface. Another possibility to cut the surface is by going from this boundary to another point on the same boundary. So now let me call this one pk. Pk. And so here it is q of pi of k. And it's the same formula, but there is a subtlety. Here, when I do this cut, it splits the surface into two. So it increases the number of boundaries instead of decreasing the number of boundaries. And in fact, it's equivalent, so splitting. And here also, by the way, here we join two boundaries, so we diminish the number of boundaries, but it was equivalent just to multiply, to changing the permutation pi to the permutation pi multiplied by the transposition 1k. And in this case, it merges two boundaries. In this case, it splits the boundary, multiplying pi. So basically, multiplying a permutation by a transposition either increases the number of cycles or diminishes the number of cycles. I mean, it may change the number of cycles. So in the case where you split, in fact, there are two possibilities of splitting. You could have split by going through an handle. If you go through an handle, and when you split, in fact, you do not disconnect the surface. The surface does not get disconnected, but it has increased the number of boundaries by 1, and the genus has dropped by 1. So you did not decrease, you did not disconnect. On the other hand, if you cut here, you really separate the surface into two disconnected surfaces. And so and here you have to sum over all possibilities of having the handles on one side or the other, of having the other boundaries on one side or the other, or on having the non-mixed traces on one side or the other. So you should take the sum of all possibilities. So let me write that as plus, and let me put a parenthesis here, plus sum over all ways of splitting, and plus, as I said, the way where you go through an handle, and it does not depend which one you go through, because they are all topologically equivalent, plus the terms with G minus 1 term, the one of G minus 1. So I hope this is clear. And that's not finished. We have more terms. And I will give an example of computation afterwards. So what are the other possibilities? So the last possibility in this picture is when you, oh, sorry, I should go do it here. The last possibility is that, in fact, I come back to the same point I started with, to the same piece of boundary. And again, if you do like I draw on the board now, this splits, this disconnects the surface. And if you would go through an handle, it would not disconnect the surface. So in addition to these terms, so inside the big parenthesis here, let me add the term where plus, plus the case where you, basically that corresponds to that. Okay, and in that case, you draw, okay, let me draw this one in more details. Okay, so in the example I take here, you have one circle. Okay, let me redraw it as a circle. So you have one circle where you have here, it was P1, but I replace it by R. Here you have Q pi of 1. No, sorry, yes, you have Q pi of 1. And so on, but you have only, I'm only taking the exterior here, so you have one handle and not two. You have one boundary here. You have a certain number of points. Okay, and you multiply it by the interior part, which is a map now where the yellow boundary, since it closes, it is no more a mixed trace. It corresponds to the single trace, so to a single. So basically, there is only R on the boundary. I should plot it as a single point. And times that, times that. Okay, and I multiply, and let me multiply by this x of R minus x of pk, which is here x of p1. Yeah, sorry. The x of, so I should not put the x of pk outside of a parenthesis. Okay. I wanted to make a shortcut, but the x of pk is inside the parenthesis because it's not the same k for different graphs. Okay, each graph has a different k. And so here, this term is inside the parenthesis, but I don't need that. So it's still inside the parenthesis. And plus, there is the possibility where you have genus minus 1. So, the possibility where the yellow line would go through the handle would be something like almost the same picture. R q pi of 1. And again, genus G minus 1. We'll have this guy, all these guys, and there is an extra R inside. Okay, so all these possibilities, so that's 5 types of graphs, and it gives the answer to everything. Let me show an example of application of this formula. Let me show examples of applications of this formula. In fact, let me keep this one here. Sorry. Let me keep this one here. So, and sorry, the values at which R, you should take residues of R, take either R, the residue at P1, or the residue at Q pi of 1, and the residue also, you shall take residue, sorry, not Q pi of 1, sorry, and R goes to Pk, or R goes to not Q pi of 1, but remember on my curve, so let's say this is my Q pi of 1 point. It has other preimages, and let me call them Q pi of 1 tilde index I, where I runs from I equals 1 to d tilde minus 1. So there are d tilde preimages. One of them is Q pi of 1, but I take all the others. And this one is the one I would call Q pi of 1 index 0. But I take only, so here I want to take only the Q pi of 1 tilde I that are all the other preimages of Y. So all the ones that have the same Y, the same value of 1. You take all the other points on the curve that have the same value of Y as this one, but the distinct from this one. So if you take the residues at all those points, compute this. So basically each of these generating function is a big rational fraction. It's a big rational fraction. This is a rational fraction. You just have to compute residues, and this gives you the answer. This can be proved by loop equations. So if you want by Tut's recursions, this is how we proved it. The proof is long, tedious. I'm not going to do it. But this is what Tut's relations give, or what loop equations give. So let me now make some explicit examples. In fact, someone yesterday was asking, can we compute the cylinder like that? We have 1x so let's say x1, x2. Let me call it p1, p2, and q1, q2. So can we compute this? Let me apply the formula. So it will be a residue in R of, let me write it here, h of p1 and q pi of 1 is q1 over h of R q1, x of p1 minus x of R, y of q1 minus y of R, times, and let's open the big parenthesis. So one possibility of cutting, so we must start here, and we must end somewhere. So we must either end here. So I can cut there. And when you cut there, what you get is this generating function. Let me, so we have Q1. P2. So we have R, P2, P2 and Q2. And by the way, this is one which is computed by the sum over C sigmas. So we have already computed that one before. Times 1 over x of R minus x of P2. Okay? Plus, and there will be another term that corresponds, the other term corresponds to the case where we come back, we start from there and we come back to the same point, and the only possibility to get something non-trivial is to go around the other circle. And when you do that, what do you get? So the exterior part is just this guy R on Q1, R on Q1 times, and the part inside is a guy with Q2, P2, and R. And this one we have not yet computed. This guy has not yet been computed. This one is simply h of RQ1. Okay. By the way, it will cancel the denominator here. This one we have not computed yet, and this one we have computed yet before. So let's compute that guy now. Well, to compute that guy, let's apply the same procedure recursively. So we have so we want to compute P2, R on Q2. And again, we should start from there and cut in a non-trivial way. And there is basically only one possibility, which is to do that. So this is a residue. So let's give a new name to the new variable. Let's call it R prime. We have h of P2, Q2, h of R prime, Q2, x of P2 minus x of R prime, y of Q2 minus y of R prime, times, and times, so the function on the outside, so we replace P2 by R prime, so is h of R prime, sorry, so it's this function here, R prime on Q2. So it is the function h of R prime Q2 times, and the function inside is, it has one non-mixed traces at R, but another non-mixed traces at R prime. So it is, if you want, the sphere. So now it's not a circle, it's a sphere, but with two marked points, R and R prime. And in my notation, this was the function W02 or omega 02 of R prime. And it is the Bergman kernel. So again, here we have a ratio that, so this cancels in the ratio. So if you want, what this guy is computing here is something like trace of 1 over x of p2 minus m1, 1 over y of q2 minus m2, times trace of 1 of x of r minus m1, the cumulant, and to the order planar. So it's typically the kind of things that you have also in free probabilities. Typically the kind of thing Speicher was writing. And you see it is equal to that residue. So let me rewrite it here. So this quantity is equal to the residue when r prime goes to either p2 or q2 tilde index i's or r. Sorry, that's all. Of h of p2 q2 over x of p2 minus x of r prime times y of q2 minus y of r prime. And sorry, I forgot dx of r prime, dx of r prime times omega 02. No, sorry. The definition of, sorry, the dx is already included in the definition of omega 02 compared to w02. R prime. Okay, so you have to compute residues at all these points. And so you see indeed the expression here has a pole. It has indeed a pole when r prime equals p2. It has a pole when r prime equals, when y of r prime equals y of q2. So it has poles at these points. And it also has a double pole at r prime equals r. Well, you could change the computation of the residues here to the computation of the other residues. The other residues would be, so this has more zeros. This vanishes not only at r prime equals p2, but at all the preimages of p2 by x. Okay, and here at r prime equals q2, I mean, okay. You can do the computation in whichever way you want, but you find something, and this, what you find is really this quantity. Let me just make a remark. This is no longer like when we had only one boundary. We had only a product of h's. A product of h's. It was a polynomial in the h's. Here, the fact that we have omega 02 typically will introduce derivatives of the h's. It will typically introduce, so we have not only product of h's, but also product of derivatives, and so on. So this gives a recursive procedure to compute any correlation functions of any mixed traces to any order, any genus, and so on. So this is what I would call the mixed traces topological recursion. Let me make a small comment. Abstraction. You see that this recursive formula just involves algebraic functions. You don't need the fact that these algebraic functions came from counting maps or came from a two-matrix model. You do not need to know what they are. So basically, give yourself, so let E of xy any polynomial of two variables. So it does not need to be related to a two-matrix model or two maps or anything. And you can make the same procedure for any E. And it will compute. So this procedure, this recursive procedure, so this mixed, so let me call it mixed TR, will give you some functions like that with those red, blue, on James G. Okay, and on more boundaries. Okay. So to every spectral curve, basically, you will be able to attach such object, a collection of such objects. So this is an abstract construction. Does it have an interest by itself? So we know that it has an interest if when E is the spectral curve of counting Ising maps. We know that it has an interest when E is the spectral curve of two-matrix model. Does it have an interest in other cases, like in Gromov-Witten invariance, like in string theory, and so on? I believe yes. However, it has not been really found. A key issue is that, okay, when you start with the two-matrix model or when you start with maps, you know in advance that all these functions are cyclically invariant, for instance. You know also that they are symmetric in all the boundaries by construction. I mean, by definition, the expectation values are symmetric. So the traces are cyclically invariant. So by construction, in the two-matrix model or in the Ising maps, you know that the result will be cyclically invariant. But if you start from an arbitrary spectral curve, will that be true? Will it still be cyclically invariant? In fact, with Séverin, we have started to do that, and we have already proved that at least, I think, okay, one boundary gene is zero. No, sorry. Okay, we have already proved cyclic invariance in a certain number of cases, but not yet in the most general case. So if we want these objects to really have to correspond to a nice geometry, they should satisfy this property for every spectral curve, the cyclic invariance and so on for every spectral curve, but this is not yet proved. This is a conjecture. Okay, what else can I say? Well, first you see that in my recursive procedure, I gave a special role to the plus sign, to the faces with plus sign, or I gave a special role to the matrix M1. But in fact, you could redo all the computations starting with matrix M2 on the minus sign. I mean, everything should be symmetric when you exchange the plus on the minus, which means that everything should be symmetric if you exchange X on Y in your spectral curve. So we believe that this method could be a method to prove symplectic invariance. In fact, in what we did with Orantin, that's more or less what we did. We used this method not for the most general mixed traces, but we showed that that indeed this is symmetric. And the key is more or less here. So I said, when you take this residue, you see you have to take residue at P2 and at the preimages of Q2. But what are the other poles? The other poles are the other preimages of P2 and Q2. So you see that somehow when you move the integration contour from the circles around these points to the circles around the complementary set of poles, you get the relation, you get the recursion for corresponding to the exchange of X and Y. And more or less that's the key. And one of the issues is, are you allowed to move those circles for integration contour across the curve to encircle the other poles? So this requires that you have a global spectral curve. And basically, we believe that the symplectic invariance should hold. I mean, this method means somehow that symplectic invariance works when you have a global spectral curve, which is compact. And we don't know if it would work when it is not compact. However, we know that in string theory, in Gromov-Witten invariance, the symplectic invariance should also work, at least for some non-compact curves. But this is just conjectures. Well, okay, so let me conclude. So what I've shown in this series of lectures, I have shown you that we can compute expectation values of arbitrary number of mixed traces in the two-matrix model. We have both exact formulas that look like determinants, and we have asymptotic formulas in the large N expansion, and we have a procedure to compute every order in the large N expansion. We have a recursive procedure that I will call mixed that I called mixed topological recursion. So the mixed topological recursion allows to compute recursively any mixed traces correlation functions to every order in powers of 1 over n by a simple recursive formula. And so I would like to thank you for your attention.
Okay, thanks, Bertrand. And are there any questions? So maybe I'd like to ask a question. So at the very end, you said how you expect this mixed topological recursion to encode some kind of enumerative invariance pertaining to curves. Do you know what are the features of these families of invariants that would make it be tuned to the mixed part of the TR? Is it
well, okay, let me do some little bit hand waving, but in Gromov-Witten theory, when you want to compute what's called open Gromov-Witten invariance, you need to, so you have a Calabi-Yau manifold, okay, let's say a toric Calabi-Yau manifold, and you fix a brane, so a Lagrangian submanifold in it. So you fix a brane, and you require that, so now you want to count in how many ways you can embed a Riemann surface of some genus and with some boundaries, such that the boundaries end up on the brane. So you have one brane, and you want all the boundaries to be on that brane. Okay. Now let's redo the same thing with, let's say, two different branes. So you want all the boundaries to end. So you want the boundaries to end on the two branes. So either they end on the first brane, and it's like non-mixed traces with, let's say, trace of powers of M1, or they end up on the second brane, then it's like trace of powers of M2. And they could also end up on somehow, okay, let me try to make a picture corresponding to what I'm thinking about. So you want to count in how many ways you can embed a Riemann surface of genus G with a certain number of boundaries into your Calabi-Yau, let me call it X, which is a certain Calabi-Yau space. It's a big space of typically 6-dimensional, so typically dim 6. And you have some branes. So let's say you have a brane L1, and you have another brane L2. And when you embed that surface here, you want that some boundaries end on L1, some boundaries end on L2, and some boundaries could end somehow like that. Okay. Okay, this is just a tentative picture, but you want somehow some pieces of some boundary to end on the first brane, and pieces of on other pieces of the same boundary to end on the second brane. So something, I mean, it's just very sketchy picture, but maybe it is pure nonsense. But this is the idea. So how can we have So this should be related to something like that, to branes, to boundary conditions that are mixed in the Gromov-Witten language. But so I don't know. I don't think this has been defined yet.
I see. So the mixed part would capture the fact that the branes could actually intersect, as opposed to the
somehow.
I see. And so then could one imagine sort of like even higher order mixing, where you have, for example, multiple branes intersecting?
Yes. Yes, of course. So here, so far, I'm doing a 2-matrix model. It would be interesting to generalize all this for multi-matrix models. I know that Orentin has started to do something about that. I don't know if it's really finished. I think it's more, I mean, I think there is still a lot to do about that. And of course, we should also recover basically the results found by people in free probabilities, at least for the planar. So in free probabilities, people are so far concerned about only the planar part, so genus 0. Here we want to go to all genus, but at least in genus 0, we should recover the same results as them. And I believe we do. The structures look very similar. You see the pictures that I was drawing is exactly what Speicher has on his t-shirt.
Okay, thanks. Any other question? I see Gaetan behind me.
So for the usual topological recursion, it is solution of loop equations. I mean, in this abstract, we call abstract loop equations in our work. And for this mixed case, some of these abstract mixed topological recursion, do you know what does it solve?
Well, yes, because we derived this recursion from the loop equations. So we know some loop equations, and I've not yet really tried to put them in a really abstract way, but yes, somehow we know.
The Schwinger-Dyson equation are always a bit, I mean, they're special, you have to do analytic continuation, do certain manipulations. But purely in terms of the spectral curve,
typically you see here, when you take these residues at these precise positions, somehow this equation came from the idea that that there was a loop equation with something that has poles only at these places and nowhere else. On the fact that there are poles nowhere else, on in fact, so poles at other locations that could have occurred, in fact, should cancel, is the loop equation, is the abstract loop equation. So the abstract loop equation is just saying that somehow the other poles should disappear. Typically, H of RQ1 has many other poles than just the ones I've cited so far. This H has many poles, and basically you want that all the other poles should in fact cancel. Okay, so I mean, okay, I'm just, okay, I mean, I believe, so we have not done it, we have not done it, but I believe it is possible to make an abstract formulation of the loop equations.
Are there any other questions? Any question from the Zoomers? No, then let's thank Bertrand again for these nice lectures.